One of the most useful aspects of matrix algebra is that it lets us compute the solution to a least squares problem we showed much earlier with an equation that's pretty easy to write, and that's what I'm writing down here. And this is not only easy to write down mathematically, but it's very easy to compute this on, using R or some other program. So this is going to be the least square estimates. Once you write out that matrices as we did in the previous module, you write down the matrices. Now you can find the solution to estimate the least square solution to estimate the parameters just by calculating this formula here. And there's also a very nice way to compute standard error of the estimates. So when we're testing to see if a particular estimated parameter is statistically significant, we're going to have to know how much it varies, and so we're going to have to compute its standard error. Right, so this is basically the t-test. We have an estimate and the standard error of that estimate, and in most situations, this is going to be normal. This is going to be well approximated with normal 0-1 distribution. So here's a formula for the standard error of parameter I, that estimate of parameter I. It includes the sample standard deviation, or when you square it's the variance, and then again the matrices show up. So I'm not going to actually compute this right now, but it's something that on a computer is straightforward to compute, and we get a general formula that lets us do it for any of the parameters in just one shot. It's very, very convenient. Now we're going to consider something that is called a cross design. So imagine you have two treatments and you create 4 groups. One receives treatment A or control, one receives treatment B, other one receives treatment C, and the 4th group receives both B and C. So we can write down a model. This is now a statistical model that tells us that if you give treatment B, if you're in group B, then there will be a difference between that group and the control, which will be parameterized with beta 1. If you're in group C, then there is an effect of being in that group that is beta 2. Now, what about the 4th group, where you get both treatment B and treatment C? And one thing we can assume is that it's an additive effect, so that you'll get the effect that B gets and you add the effect that C gets. It's done with matrix notation over here. So we have for group A, you have these 2 samples. So you have 1 times beta 0, and the other 2 get multiplied by 0. So there's no beta 1 or beta 2. So therefore, beta 0 is the effect of being in the control group. If you're in the 2nd group, then you get a beta 1. So it's beta 0 plus the effect of being in group B. That's beta 0 plus beta 1, and then no beta 2. And that gets you up to here. This arrow here shows you beta 1. Now, what if in group C, you get that other treatment. You don't get beta 1, and your average value should be beta 0 plus beta 2. So you have a 0 for the beta 1, and that gives you this quantity here. Now, what about in the 4th group, group D? There we're assuming that the effects are additive. So we have beta 0 plus beta 1 plus beta 2, and that is shown in the matrix algebra notation by just noticing that you have 1, 1, 1, and you add up these 3 numbers, and that gets you up here. That's beta 1 plus beta 2. Okay, now what if the effects aren't additive? That could very well be that the 4th group is not where it's expected. It's not at the level of adding beta 1 plus beta 2. In this case, we can use a separate model that now gives us a different mean for each group. We have 4 possibilities, and in the experimental design and linear algebra approaches, we call that 4th term the interaction. So now the model is written out like this, and let's see what each one of these it represents. So just like before, we have in the first group, group A, you just have beta 0. In the second group, you have beta 0 plus beta 1. In the third group, you have beta 0 plus beta 2. Now, in the fourth group, you have something new. You have the additive effects, so it's beta 0 plus beta 1 plus beta 2. But notice that if we just use that model, we would predict the data to be here. But it's not there. It's actually a little bit higher. So it looks like adding these two treatments has an interaction effect that makes the values even higher than we would expect had we just added. And that term now is this beta 1 colon 2 that is represented by this quantity here. So by fitting this model, we get these four estimates, and using those 4 estimates, we can actually predict the mean levels for each of the 4 groups. And we can interpret that last parameter as an interaction effect, the effect that you get on top of just adding the first 2 main effects. All right, now you might have heard of these linear models in other contexts. The most common one is in epidemiology, where you hear a lot of media reports saying, you know, we controlled for age, race, and sex, and they still found an effect. And so when they say that they control for this and that, basically what they're saying is that they are fitting a linear model that includes all those possible explanatory variables as variables in the model. And they fit them, and they hope that corrects for them, and then they report the difference that they're actually interested in. But one word of caution, we see this very often, that people that use linear models, they say we have to correct for age, and age is a continuous variable, and I'm using as an example. So they just stick it into a linear model. So now what you're saying is that you have a baseline effect, and then for every year older that you are, your measured value should increase by beta age, this beta here. Right? And that's a very strong assumption, right? You're saying that every time every year you add it on. So you're assuming it's a line. It's not a curve. It's not a line that flattens out. It's a line. And if it's anything else, then the model is going to be wrong. So that's something that you want to be careful about, that when you use these linear models, don't forget that they're representing something real. You want to understand what it is that the linear models are representing, and that you're not doing something nonsensical and just running with it. And one thing to remember is that the computer is going to give you an answer, even if the model is wrong. It's going to run. The computer's not going to say that model doesn't make sense. It's just going to give you the estimates, the confidence intervals, standard errors, and p-values. So keep that in mind when you use linear models. Now, we've seen how useful linear models can be. In the labs, we're actually going to use them. We're going to do a lot of things with them. We're going to use a package called Lima to do a lot of this, and we're also going to show you how powerful R can be at doing some of these matrix computations.